In the previous video, we have derived an expression for Biot-Savart law, which was mu0 ideal sin theta divided by 4 pi r square. Now, we will apply the equation here to get magnetic field due to a current carrying circular loop at its axis. Okay, so this is the current carrying circular loop. Let's say current is going in this direction. So, it's downward here, it is upward here, and I am keeping it in this way. That is the picture I have drawn here. Now, I want to get the value of magnetic field at this position. Okay. Now, we will apply the Biot-Savart principle here. Before that, see, it has been defined, Biot-Savart law has been defined for a small current carrying element, right? mu0 ideal sin theta divided by 4 pi r square. This is the value given for magnetic field as per Biot-Savart law. So, which current carrying element do I consider here? Should I consider here? I will consider this one. I can consider any current carrying element. Let's say I am considering this for the time being. So, a small element here. Now, at this point, what will be the direction of magnetic field? I have to apply right hand thumb rule, right? So, the current carrying element is in this way and current is going in this direction, right? In this direction. Here it is downward, so current have to be in this direction here, in this direction here, in this direction here. So current is in this way. Now this is my position vector. So if I am keeping it in this way, magnetic field will be in this direction. So at this point, due to a small element here, at this point, magnetic field will be in this direction. It will be perpendicular to the line connecting the current carrying element with the point. Okay. Now, one more thing. What is the angle in between these two current carrying element and my position vector? See, here it is, I mean, it looks like some inclined at some angle of theta, but actually current carrying element is in this direction here. Okay, towards me. And my position vector is in this way. Though there are some angle formed here, but when you see in this perspective, these two angles are 90 degrees. See, this angle makes 90 degrees. Here, what is the angle between my pen and the tangent here? It's 90. Here also it is 90. I mean, how to get the value? Angle in between the tangent here and this one. That is 90. Here also it is 90. Here also it is 90. See, everywhere it is 90. It's two plane, right? One is in this plane and another one is in this plane. So, these two planes are making 90 degree always. Okay. See, here, once again I'll repeat it. Here, now tangent is this one. Okay. See my finger. Tangent is this one and here it is 90. Now I'm rotating. Till it is 90. Till it is 90. See, here also it is 90. See, this is the angle here. Here, see, this is the angle 90. If it is inclined in this way, this is the angle. Inclined in this way, see, till the angle is 90 degrees. So, the angle in between DL and this one is 90 degrees. So, there are three planes involved, so that makes some confusion, but here the angle R makes L, the angle that R makes with L is 90 degrees. So, I will apply the equations here. B is equal to mu0 ideal sin theta divided by R square. But the theta that is in between DL and R is 90 degree here. So that will become mu0 ideal by R square. Since sin theta is equal to sin 90 is equal to 1. mu0 ideal divided by, mu0 by 4 pi. Okay. mu0 by 4 pi is the constant. Ideal sin theta by R square. So mu0 by 4 pi is a constant here. Okay. Ideal by R square. Sin theta will not be there. Now, this is the direction of magnetic field, right? Now, this magnetic field can be split into two directions. One is in this way, another one is in this way. See, now we know that these two are 90 degrees, which means this one and this one make an angle 90 degrees. And this one also make 90 degrees. So, if this angle is theta, this one also will be theta. How can you check? Just rotate it here. So, for every angle you are rotating with my finger, I am rotating 1 degree. So you also will be rotating 1 degree. Then only this will be 90 degree and this will be. So this is 90 degree here. This one is also 90 degree. If this angle is theta, this also has to be theta. Just rotate it here. So this will be in this direction. Every 1 degree you are making here, you will be making here also by rotating it in this direction. That's how you can visualize and understand. So if this angle is theta, this one also will be theta. Now B can be split into two directions. The one which is having theta will be B cos theta and this will be B sin theta. Now the same current, the current from here that will go to here and it will go inward here. Inward. So what will be the direction? So this is the direction of current and at here it will be in this direction. At this point. But B will be the same value. Why? It is the same current. Even the distance is also same. R is same. Even the current carrying element, I am taking the same thing, ideal. So here also magnetic field will be same. But it is in the different direction. Here it is in this direction. Here it will be in this direction. Now this also can be split into two. One is, so same way we have taken theta here and here. Here also this will be theta and here also this will be theta. Okay, so if this is theta, this will be B cos theta and this will be B sin theta. Now see, when we have taken two different directions, two different positions, we got B sin thetas are added in the same direction. But what has happened? B cos theta, this B cos theta has got cancelled by this B cos theta. So any two positions if you are taking in such a way that are diametrically opposite, this B cos theta will be cancelled, only B sin theta will be there. Okay. So literally when you are, so this is here we are only finding magnetic field created due to the small element dl, right? Now at the same time we have to find magnetic field at this position created by another dl, another dl, another dl, another dl. So after finding all the dl elements, we have to add it and we will be getting the net magnetic field here. But one thing is for sure, every element's cos theta component will be cancelled. We will have only sin theta. Okay. Now what will be the equation? This is the magnetic field, but net magnetic field will be along this direction. And what will be the value? Is equal to B cos theta, B sin theta. So what is the situation? The situation is consider 2 points which are diametrically opposite. These two opposite. So when we have considered, we got the value as B sin theta plus B sin theta, 2B sin theta. So anyway, B sin theta combined with the value which is present after on each dl element. Okay. Now we have to integrate to get B total net magnetic field at the point P. This is the point P. What we have to do? We have to add up all B sin theta created by each and every dl element. What is this process? We have to integrate. So integral. This is circular integral, which means we are integrating for the complete circle, for the complete loop. Of what value we are integrating? B sin theta. This is B. Its sin theta component we are integrating. So that will be mu0 IDL by 4 pi r square. This is B. Its sin theta component. Now sin theta. What is sin theta from here? This is a right angle triangle. So sin theta is opposite by hypotenuse. So what is the value of hypotenuse? If this one is A, this one is X. I'll introduce what is A. A is nothing but radius of the circular loop and X is at a distance X away from the center. So we are finding the magnetic field at a point which is X distance away from the center of the coil. Okay. So that is A and X. A is radius of the coil and X is distance of P from center of the coil. So if these two angles sides are not, I can easily get the value as A square plus X square, root of A square plus X square. That is the hypotenuse here, either base and height. Okay, so R square is nothing but this square, right? R is this one, the distance in between these 2 points, in between DL and the position. So its square, R is this one, its square will be a square plus x square. So I am substituting the value mu0 I dl divided by 4 pi r square is a square plus x square from the diagram, and sin theta is nothing but opposite by adjacent. So opposite is a, adjacent is root of a square plus x square. Okay, now we are keeping it. So here, what are the so to do integration, first we will take the constant out, we will only keep the variable. But which are the constant here? User is anyway constant. I current passing through this, everywhere it is constant. Yeah, this one will never change unless the coil is being changed. And A is a constant, X is also constant at this position. Only the variable is dl, right, on this integration. So what we will do, we will take the term out. So this is a square plus x square the whole power 1. Now root means a square plus x square the whole power 1 by 2. So see, a power m into a power n is a power m plus n. So similarly, one term power 1, another term raised to half, we can add these two. So next it will become integral of mu0 I a into dl divided by 4 pi into, this will become a square plus x square the whole power 1 into a square plus x square the whole power 1 by 2 whole power 3 by 2. Now this value will be, I can take the common term of mu0 I, a is a common term and 4 pi is also common. These are constants, okay? Constant 3 by 2. I have taken all these out. I have only integral dl. Now if I am adding all the dl, that is nothing but the circumference, right? So integral dl will be 2 pi a. If a is the radius, so mu0 I a into dl is 2 pi a divided by integral of that is divided by 4 pi into a square plus square the whole power 3 by 2. Okay, now I am going to rewrite it. Okay, what is the equation? We got E is equal to mu0 into, what is a into pi a square for this one? Pi into a square is nothing but pi r square here, right? Pi into a square, that is nothing but area. So pi a square I am going to rewrite as area. So the value will be mu0 by 4 pi. It's a constant, right? I take it out. Then I have I, then pi a square is there. I have 2 here, so 2 I a divided by a square plus x square the whole power 3 by 2. Now we have only one coil here, right? If there are n coils, then I have to multiply it with n times. For n coils, Bn is equal to mu0 by 4 pi into 2 into n I a divided by a square plus x square the whole power 3 by 2. Now this NIA is taken as magnetic moment. Okay, you can make a note of it. Magnetic moment has been defined as NIA. Number of terms will be current into area. So that will become now mu0 into 2m divided by 4 pi into a square plus x square the whole power 3 by 2. Now we will take two special cases. One is at the center and one is very far away from it. So first case at the center. So I will arrange this one also. Now special cases. This is very important, okay? Net magnetic field. Special cases. B at center and B is very far away on the from the axis. On the axis. From what? From the center. The center. So B at center. At center, when the point comes to center, x will become 0. See, x will become 0. So x is equal to 0. Substitute in this equation. Bn will become mu 0 into 2m divided by x is 0. So this will become a square the whole power 3 by 2. 2 and 2 will cancel, that will become a cube. 4 pi a cube. Mu 0 by mu 0 into 2m, 4 pi, x will become 0, a square the whole power 3 by 2 to x. Very important, dx and y. Now be very far away from this, that is x is very greater than 2. So a can be ignored, a is moved to 0, the value will be mu 0 into b is equal to mu 0 into 2m divided by 4 pi, x is greater than a is 0. So we have x square the whole power 3 by 2, that is 8. So one thing is very sure, that when we are increasing the value of x, magnetic field decreases. See, B is inversely proportional to x cube. This is very important. Which means, at where will be the maximum value? Maximum value is at the center. So when we are plotting a graph, magnetic field from here, as it go out, it decreases. In this side also, magnetic field will be decreased. Maximum value will be at center, when magnetic field decreases, magnetic field decreases. So this can be compared as magnet. Where will be the maximum magnetic field? Here. Now from here, intensity of south pole decreases. So as we go on the left, intensity of north pole decreases. Maximum will be on the magnet. So this can be compared as magnet, which means we have one polarity here, another polarity here. Now I will tell you how to get the value of polarity. So these are very important. Make a note of it. We are going to polarity. So we have compared it with magnet. Magnet is a dipole. How? Because it has got two poles, north and south. So magnet is similar to this thing. On both the sides we have magnetic field, and that means in the same way this changing is magnetic field changing is magnet. Okay, permanent magnet. Now, if the current is going in counterclockwise direction, anti-clockwise direction, then you can mark a counterclock here and mark counterclockwise direction. So that is north pole. Okay, now when you have current going in this direction, that is south pole. So here, when I got a current, let's say this current carrying conductor. Now I see current going in clockwise direction. But at the same time, when I am seeing it from this side, this will be counterclockwise direction. So it can be seen. So for me, let's say the current is going in this direction. You can check it from your end. Current is going in clockwise direction. Now when you see that, you will see current going in. See how the finger is moving. With respect to me, this is clockwise. Now with respect to you, it is counterclockwise, which means when it is clockwise, for me it is south. Okay, this side is south, but you are seeing the north pole, though it is current carrying conductor. Now for a conductor, you can't split it, right? Okay, which means north and south pole cannot be split, which means in magnetism, everywhere you can see dipole, north and south. You can't separate north from south. Okay, like you have a current carrying one coil, but for you it is south, for me it is not. The moment magnetic field is created, there are two poles existing in that space. One is north and south. There cannot be magnetic singular pole, that is one pole possible. Existence of singular pole is not possible. Always it is monopole. Sorry, not singular pole. Magnetic monopole doesn't exist. But in the case of charges, monopole exists, positive charge and negative charge. When positive and negatives are combined, that two equal in magnitude, then I can say it is electric dipole. But with magnet, it is always dipole. Magnetic monopole doesn't exist. Okay, thanks.